The s-block elements of the periodic table are those in which the last electron enters the outermost s orbital. The s-block of the periodic table constitutes group 1 and group 2. The elements of group 1 of the periodic table are known as the alkali metals because they form hydroxides on reaction with water, which are strongly alkaline in nature. Group 1 of the periodic table consists of 6 elements: lithium, Li, sodium, Na, potassium, K, rubidium, Rb, cesium, Cs, and francium, Fr. All the alkali metals have one valence electron. The general electronic configuration of the valence shell of alkali metals is Ns1. They are never found in free state in nature because they readily lose electron to give monovalent M+ ions. The electronic configuration of alkali metals is shown. The atomic radius of the alkali metals increases from top to bottom in a group and decreases from left to right in a period. The ionic radii of the alkali metals are much smaller than their atomic radii. The ionization enthalpies of the alkali metals are low. Ionization enthalpies decrease down the group. The hydration enthalpies of alkali metal ions decrease with increase in ionic radii. After reviewing this digital content, you will be able to explain the general characteristics of the alkali metals. Describe the physical properties of alkali metals. Explain the chemical properties of alkali metals. List some uses of alkali metals. Identify compounds of the alkali metals and their general characteristics. Define anomalous properties of lithium. Describe the manufacture, properties and uses of industrially important sodium. Identify the biological importance of sodium and potassium. Assessment. Describe the general characteristics of the alkaline earth metals. Identify the physical properties of alkaline earth metals. Explain the chemical properties of alkaline earth metals. List some uses of the alkaline earth metals. Describe the general characteristics of the compounds of the alkaline earth metals. Identify the anomalous behavior of beryllium. Describe the manufacture, properties and uses of industrially important calcium compounds. Identify the biological importance of magnesium and calcium. There is a regular trend in the physical and chemical properties of the alkali metals with increasing atomic numbers. Alkali metals are shiny, soft, highly reactive metals and readily lose their outermost electron. They can all be cut easily with a knife due to their softness. These elements have low density which increases down the group from lithium to cesium with an exception at potassium. Potassium is lighter than sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonding because of the presence of only one valence electron in them. The melting and boiling points decrease down the group. The alkali metals and their salts impart characteristic color to an oxidizing flame because the heat from the flame excites the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is emission of radiation in the visible region. Electronegativity is the tendency of an atom or a functional group to attract electron towards itself. Alkali metals have lowest electronegativity. Electronegativity decreases from top to bottom and increases from left to right. No more. Francium is a highly radioactive element. It has a half-life of only 21 minutes. Exposing a shiny surface of the alkali metal tarnishes rapidly in air due to oxidation. Because of their high reactivity, the alkali metals must be stored under oil to prevent reaction with air. Lithium forms monooxide, sodium forms peroxide, and other metals form superoxides. The alkali metals react vigorously with water to form hydroxide and hydrogen gas. They become more reactive as you go down the group. The alkali metals also react with hydrogen to form compounds known as hydrides. The alkali metals react directly with the halogens to form halides. General reaction is shown where M is an alkali metal and X is a halogen atom. Look at the reaction of alkali metals and halogens. Lithium, sodium, potassium, rubidium and cesium on reaction with chlorine give lithium chloride. Sodium chloride. Potassium chloride. Rubidium chloride. And cesium chloride respectively. All the alkali metals are strong reducing agents because they readily donate electrons. They are quite reactive, even reducing water. On reaction with ammonia, the alkali metals form amides. The solution of metal and liquid ammonia is deep blue in color. An example is shown. Lithium is often used in batteries. Lithium metal is used to make useful alloys. Pure sodium is used in sodium vapor lamps. Sodium compounds have many uses as well, the most well-known compound being table salt. Sodium is also used in soap as salts of fatty acids. Liquid sodium metal is used as a coolant in fast breeder nuclear reactors. Potassium has a vital role in biological systems. Potassium chloride is used as a fertilizer. Its hydroxide is used in the manufacturing of soft soap. It is also a good absorbent of carbon dioxide. Rubidium and cesium are often used in atomic clocks. Cesium atomic clocks are extraordinarily accurate. Cesium is used in devising photoelectric cells. All the common compounds of the alkali metals are generally ionic in nature. Sodium and chlorine react to form sodium chloride, an ionic compound. The oxides of the alkali metals are easily hydrolyzed by water to form the hydroxides. General reactions are shown. The peroxides and superoxides of alkali metals act as oxidizing agents because they form H2O2 and H2O2 and O2 respectively on reaction with water. The hydroxides are obtained by the reaction of the oxides with water. The alkali hydroxides are lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, and cesium hydroxide. They are all white crystalline solids. Almost all alkali metal hydroxides dissolve in water with the evolution of heat. The alkali metal hydroxides are the strongest of all the bases. All alkali hydroxides are very corrosive. The alkali metal halides are colorless crystalline solids, although finely ground powders appear white. The alkali halides are lithium halide, sodium halide, potassium halide, rubidium halide, and cesium halide. Here, X can be fluorine, chlorine, bromine, iodine. The alkali halides are ionic in nature. All these halides have high melting points. The melting and boiling points always follow the trend. Metal fluorides greater than metal chlorides, greater than metal bromides, greater than metal iodides. These halides can be synthesized by treating their carbonates, hydroxides, with hydrogen halide. Have a look at the following reactions yielding lithium chloride, sodium chloride, and potassium chloride. The alkali metals form salts with all the oxo acids. Some salts of alkali metals and oxo acids are lithium carbonate, lithium hydrogen carbonate, and sodium carbonate. The salts of alkali metals and oxo acids are generally soluble in water. They are stable to heat except lithium carbonate. On heating lithium carbonate, more stable lithium oxide and carbon dioxide are formed. No more. An oxo acid is an acid that contains an oxygen atom bonded to a hydrogen atom and at least one other element. Examples of oxo acids: carbonic acid, sulfuric acid, etc. The anomalous behavior of lithium is due to the extremely small size of its atom and ion, high polarizing power of lithium ion, which results in the covalent character of its compounds, non-availability of vacant d orbitals in the valence shell, least electropositive character, and highest ionization energy as compared to other alkali metals. The melting point and boiling point of lithium are comparatively high. Lithium is much harder than other alkali metals. Magnesium is also a hard metal. Lithium reacts with oxygen least readily to form monoxide, whereas other alkali metals form peroxides and superoxides. Lithium hydroxide and magnesium hydroxide are less soluble in water and are weak bases. Hydroxides of other alkali metals are strong bases. Due to their appreciable covalent nature, the halides and hydroxides of lithium and magnesium are soluble in organic solvents. Unlike the elements of group 1, but like magnesium, lithium forms nitride with nitrogen. Lithium chloride is deliquescent and crystallizes as a hydrate. Other alkali metals do not form hydrates. Magnesium also forms hydrate. The carbonates, hydroxides, and nitrates of lithium as well as magnesium decompose on heating. The corresponding salts of other alkali metals are stable towards heat. Lithium nitrate on heating decomposes to give lithium oxide, whereas other alkali metal nitrates decompose to give the corresponding nitrites. Lithium carbonate, lithium fluoride, and lithium peroxide are the only alkali metal salts which are insoluble in water. The corresponding magnesium compounds are also insoluble in water. It is a mild antiseptic for skin infection. Sodium carbonate, sodium hydroxide, sodium chloride, sodium bicarbonate. Preparation of sodium carbonate by Solvay process. Carbon dioxide passes through brine, a concentrated aqueous solution of sodium chloride, and ammonia. CO2 is produced by heating of limestone. The sodium bicarbonate that precipitates out in reaction 1 is filtered out from the hot ammonium chloride. The solution is then reacted with quicklime. The ammonia from this reaction is recycled back to the initial brine solution reaction. The sodium bicarbonate precipitated from reaction 1 is then converted to the final product. Sodium carbonate is a white crystalline solid which exists as decahydrate. This is also called washing soda. On heating, the decahydrate loses its crystalline water to form monohydrate. Above 373 Kelvin, it becomes completely anhydrous and changes to white powder called soda ash. It is used in water softening, laundering, and cleaning. It is used in the manufacture of glass, soap, borax, and caustic soda. It is used in paper, paints, and textile industries. Sodium chloride. The most abundant source of sodium chloride is seawater. Common salt is generally obtained by evaporation of seawater. Molecular formula is NaCl. This salt contains sodium sulfate, calcium sulfate, calcium chloride as impurities. For the purification of salt, it is dissolved in minimum amount of water and then filtered to remove the insoluble impurities. Then this solution is saturated with hydrogen chloride gas. Crystals of pure sodium chloride separate out. It is used as a common salt. It is used for preparation of sodium peroxide, sodium hydroxide, and sodium carbonate. Sodium hydroxide. Preparation. A brine solution is electrolyzed using a mercury cathode and a carbon anode in Castner, Kellner shell. Sodium metal discharged at cathode combines with mercury to form sodium amalgam. Chlorine gas is evolved at the anode. The amalgam is treated with water to give sodium hydroxide. Sodium hydroxide is a white, translucent solid. It is readily soluble in water to give a strong basic solution. Crystals of sodium hydroxide are deliquescent. It is used in manufacturing of soap, artificial silk. It is used in petroleum refining, in purification of bauxite, etc. Sodium hydrogen carbonate. Molecular formula is NaHCO3. Preparation. Sodium hydrogen carbonate is prepared by saturating a solution of sodium carbonate with carbon dioxide. Sodium hydrogen carbonate is known as baking soda. It is a mild antiseptic for skin infection. It is used in fire extinguisher. It is amazing to know that a normal 70 kilograms man contains about 90 grams of sodium, 170 grams of potassium, compared with only 5 grams of iron and 0.06 grams of copper. Sodium ions are found primarily on the outside of cells, being located in blood plasma. These ions participate in the transmission of nerve signals, in regulating the flow of water across cell membranes, and in the transportation of sugars and amino acids into cells. Sodium and potassium, although similar chemically, differ quantitatively in their ability to penetrate cell membranes, in their transportation mechanisms, and in their efficiency to activate enzymes. Potassium ions are the most abundant cations with cell fluids, where they activate many enzymes. Potassium ions participate in the oxidation of glucose to produce ATP. Sodium ions are responsible for the transmission of nerve signals. The sodium-potassium pump operates across the cell membrane, which consumes more than 1/3 of the ATP used by a resting animal, and about 15 kilograms per 24-hour in a resting human. Group 2 of the periodic table consists of 6 elements. Beryllium, Be, magnesium, Mg, calcium, Ca, strontium, Sr, barium, Ba. These, except beryllium, are commonly known as alkaline earth metals because their oxides and hydroxides are alkaline in nature, and these metal oxides are found in the Earth's crust. All the alkaline earth metals have 2 valence electrons. The general electronic configuration of valence shell of alkaline metals is Ns². Like alkali metals, the compounds of these elements are also predominantly ionic. The electronic configuration of alkaline metals is shown. The atomic and ionic radii of the alkaline earth metals are smaller than those of the corresponding alkali metals in the same periods. Within the group, the atomic and ionic radii increase with increase in atomic number and decreases from left to right in the same period. The alkaline earth metals have low ionization enthalpies due to fairly large size of the atoms. Since the atomic size increases down the group, their ionization enthalpy decreases. The first ionization enthalpies are higher than those of the corresponding group 1 metal, but the second ionization enthalpies of the alkaline earth metals are smaller than those of the corresponding alkali metals. Like alkali metals, the hydration enthalpies of alkaline earth metal ions decrease with increase in ionic radii size down the group. The alkaline earth metals in general are silvery white, lustrous, and relatively soft, but harder than the alkali metals. beryllium and magnesium appear grayish. The alkaline earth metals have high electrical and thermal conductivities. The melting and boiling points of the alkaline earth metals are higher than the corresponding alkali metals. Calcium, strontium, and barium impart characteristic brick red, crimson, and apple green colors, respectively, to the flame. The electrons in beryllium and magnesium are too strongly bound to get excited by flame. Hence, these elements do not impart any color to the flame. The electropositive character increases down the group from beryllium to barium, or the electronegativity decreases down the group from beryllium to barium. Beryllium and magnesium do not react with oxygen and water because of the formation of an oxide film on their surface. However, beryllium and magnesium burns brilliantly on ignition in air to give their oxides and nitrides. Calcium, strontium, and barium are readily attacked by air to form oxides and nitrides. Calcium, strontium, and barium also react with water with the evaluation of heat to form hydroxides. All the alkaline earth metals combine with halogen at elevated temperatures, forming their halides. All the alkaline earth metals, except beryllium, combine with hydrogen upon heating to form their hydrides. Here, M is an alkaline earth metal which can be magnesium, calcium, strontium, or barium. The alkaline earth metals readily react with acids, liberating dihydrogen. Like alkali metals, the alkaline earth metals are strong reducing agents. However, their reducing power is less than those of their corresponding alkali metals. Like alkali metals, the alkaline earth metals dissolve in liquid ammonia to give deep blue black solutions, forming ammoniated ions. Beryllium is mostly used for military applications. Beryllium oxide is used as a high-strength electric insulator and heat conductor. Magnesium forms alloys with aluminium, zinc, manganese, and tin. A suspension of magnesium hydroxide in water, called milk of magnesia, is used as antacid in medicine. Calcium is used in the extraction of metals from oxides, which are difficult to reduce with carbon. Radium salts are used in radiotherapy, for example, in the treatment of cancer. The alkaline earth metals form compounds which are predominantly ionic, but less ionic than the corresponding compounds of alkali metals. Magnesium reacts with chlorine to give an ionic compound, magnesium chloride. The oxides of the alkaline earth metals, except beryllium, are easily hydrolyzed by water to form the hydroxides. Beryllium oxide is amphoteric, while oxides of other elements are basic in nature. The alkaline earth metal hydroxides are less basic and less stable than the alkali metal hydroxides. Beryllium hydroxide is amphoteric in nature as it reacts with acids and alkali both. The halides of the alkaline earth metals are ionic in nature. The alkaline halides are beryllium halide, magnesium halide, calcium halide, strontium halide, barium halide, where halide can be fluorine, chlorine, bromine, iodine. Beryllium halide is covalent and soluble in organic solvents. the tendency to form halide hydrates gradually decreases from magnesium to barium. Beryllium chloride has a chain structure in the solid state. The alkaline earth metals form salts with all the oxoacids. Carbonates of alkaline earth metals are insoluble in water. All the carbonates of these metals decompose on heating to give carbon dioxide and oxide. The sulfates of the alkaline earth metals are all white solids and stable to heat and soluble in water. The nitrates are made by dissolution of the carbonates in dilute nitric acid. All of them decompose on heating to give the oxide. The anomalous behavior of beryllium is due to the extremely small size of its atom and ion, high ionization enthalpy, which results in the covalent character of its compounds, non-availability of vacant d orbitals in the valence shell. The oxide and hydroxide of beryllium, unlike the hydroxides of other elements in the group, are amphoteric. Like aluminium, beryllium is not readily attacked by acids because of the presence of an oxide film on its surface. Beryllium hydroxide dissolves in excess of alkali to give berylate ion, just as aluminium hydroxide gives aluminate ion. The chlorides of both beryllium and aluminium have Cl bridge. The chlorides of both beryllium and aluminium are soluble in organic solvents. Both the chlorides are strong Lewis acids. They are used as Friedel-Crafts catalysts. Beryllium and aluminium ions have strong tendency to form complexes. Industrially important compounds of calcium include calcium oxide, calcium hydroxide, calcium sulfate, calcium carbonate, and cement. Preparation of calcium carbonate or quicklime. It is prepared on a commercial scale by heating limestone. Calcium is a white amorphous solid. It absorbs moisture and carbon dioxide. On reaction with water, it gives calcium hydroxide. Being basic oxides, it combines with acidic oxides at high temperatures. It is an important primary material for manufacturing cement. It is employed in the purification of sugar. Calcium hydroxide is prepared by adding water to quicklime. It is a white powder soluble in water. The aqueous solution is known as lime water. When CO2 is passed through lime water, it turns milky due to the formation of calcium carbonate. On passing excess of carbon dioxide, it forms calcium hydrogen carbonate. On reaction with chlorine, it forms bleaching powder. It is used to whitewash. It is used in glass making. Calcium carbonate occurs in nature in several forms, like limestone, chalk, marble, etc. It can be prepared by passing carbon dioxide through slaked lime or by the addition of sodium carbonate to calcium chloride. Calcium carbonate is a white fluffy powder, almost insoluble in water. It decomposes to evolved carbon dioxide on heating at 1200 Kelvin. It reacts with dilute acids to liberate carbon dioxide. It is used as building material. It is used as an antacid, mild abrasive in toothpaste. Plaster of Paris is a hemihydrate of calcium sulfate. It is obtained when gypsum is heated to 393 Kelvin. Above 393 Kelvin, no water of crystallization is left, and anhydrous calcium sulfate is called dead burnt plaster. On mixing with an adequate quantity of water, it changes into hard solid. It is used in building industry as well as plasters. It is also used for immobilizing the affected part of an organ where there is a bone fracture or sprain. Portland cement is an important building material. Cement is a product obtained by combining a material rich in lime with other materials such as clay, which contains silica, along with the oxides of aluminium, iron and magnesium. When mixed with water, the setting of cement takes place to give a hard mass. An adult body contains about 25 grams of magnesium and 1200 grams of calcium. All enzymes that utilize ATP in phosphate transfer require magnesium as the cofactor. Chlorophyll contains magnesium. About 99% of body calcium is present in bones and teeth.